a lecture series on differential equations. We established some intuitions that if I have a real life problem here, let me use a green. If I have a real life problem here, you know that you have to solve the problem. Realistically, you have to solve the problem to obtain a solution. Right. And we also established the fact that we can model the problem using a differential equation for the real world problem. In the same way, you have to solve the differential equation and obtain a solution. In this lecture series, I want to assume that yes, I have obtained a solution to the differential equation. As to how it was solved, we'll get through that in the subsequent lecture videos. Now, if the solution has been found, is it indeed a solution to a differential equation? That is the question we are asking. Is this solution indeed a solution, or it is, let me use the word, it is fake, or it is not? Alright, so that leads us to the next objective in my slides called the solution to differential equations. Solutions to differential equation. What is this? My slides has a definition that a solution to a differential equation on an interval is a function that satisfies the differential equation in question. In simple terms, I have a differential equation here and I have obtained a solution here. This is a solution to the differential equation if and only if it is satisfying the differential equation. So this goes back here. So the solution is a solution to a differential equation if and only if the key term here is that it must satisfy the differential equation and any other information that comes with it. Okay, other than that, it fails to be a solution. Okay, now with the solution here, we have two forms of the solution. There's a general solution and a particular solution. I'll use diagram to just explain what this general solution is. So assuming I have my axis, I draw a graph x and y. I have solution 1, solution 2, solution 3, 4. This is a general solution. But with a particular solution, I have the same x-axis and y-axis. I can just draw one of them. That is a particular solution. So I can use the word specific, or I think unique should also do. Unique solution, specific solution. That is particular solution. I hope that is clear. So we have a simple one solution to talk about other than the general solution. So in my slides, it says it has arbitrary constants C in the solution. That's another way. As I pictorial view, the solution will have some terms of C's or constant in it. But the particular solutions comes with some conditions that will help you obtain that unique or specific solution. Okay. So the question is, how do I get that unique solution, or that certain, let me use another word, certain solution? I'm very certain about it. The particular solution comes from two forms of problems. There's IVP, so I think I can do away with this graph here to make the sheet clean a bit. The particular has IVP, that is initial value problem, as you can see on the slide. Initial value problem. And then the B stands for boundary value problem. The initial problem has the solution specified at the same point, at one point. So that is the key word here, at the same point in the solution of the problem. The boundary has its solution or its conditions specified at different points of the problem. So as you can see from the table, or let me see the picture, it says some conditions are defined as x0 equals to something, and then x prime as 0 equals to something. The points are 0 and 0, so they are the same. But if I come here, have x as 0 equals to something, let me do away with this one, and then I have x at 2. These are two different points being specified, 0 and then 2, so they become boundary problem. This is 0 and 0, the same initial point. Let me also clarify that you can have it's not always 0 at a point, depends on the problem you are solving. Some of them can start at 2 and then x prime at 2, x prime prime at 2. This is still an initial value problem because all the points are defined at 2. Again, the number of conditions to add depends on the order of your problem. Let me quickly take you through that. If my order of the differential equation, as we've already gone through, is order 2, the highest order is 2, it means I will need 2 conditions, whether it is IVP or BVP. If the highest order is 3, I will need 3 conditions, in whether it is the initial or the boundary. If the highest order is 1, it means I'll next need 1 condition. It can be IVP, it can be the boundary. Alright, so that is it for these two guys. I told you that we want to assume we have already obtained the solution. We want to test that it is indeed a solution. So we want to test the solution. And how do we do that? That is the last thing to talk about in this video. The solution test is a direct substitution into the differential equation. As simple as that. It is a direct substitution. So you look at the solution you have. It says differentiate to the highest derivative. If my highest derivative is 2, it means I'll differentiate it twice. If the highest derivative there is 3, I'll differentiate it thrice. Or how do we pronounce that? So I'll have it 3 times. If the highest order is 1, I'll just differentiate it once. And so on and so forth. So quickly, let's go through some examples here. I'll first do a general solution and one particular solution, and that'll be it for the day. Differential equation, solution, and solution type. I said what is the class here. I hope you can do that. It's a second order. Is it linear? Yes. Second order linear. Is it homogeneous? Yes. Second order linear homogeneous ordinary differential equation. I hope you agree to this. Okay. It says you are given a solution as this. Prove that it is indeed a solution. Now the solution type is general because I have some arbitrary constant terms here. So this is a general solution. Or you can also say that the equation you have do not have any conditions attached to it. So it is a general solution. How do I prove that? Because the highest order is 2, I differentiate it twice. The first derivative gives me, if you differentiate cos, you get negative sign. If I differentiate sign, I get positive cos. I differentiate again. Y prime prime means differentiate this y prime. Please note that. If I should differentiate again, I'm differentiating y prime. I'll have negative c1 cos x minus c2 sin x. So I'll substitute equation 1 and equation 2 into the differential equation. The differential equation does not have y prime. It's just y and y prime prime. So let's do a substitution. I have negative c1 cos x minus c2 sin x for the y prime prime plus y part c1 cos x plus c2 sin x. So let's group like terms and see what we can do. You realize that this and this cancels out, and this also cancels out, which is equal to 0 as we expect. It says the equation is equal to 0, hence it is a solution to the differential equation. So that's it. So hence it is indeed a solution to a differential equation. In the second example, this is a second order linear homogeneous equation. You can verify that for me. The solution is this. It's a test whether it is indeed a solution or not. Because the highest order here is 2, it means I have to differentiate my solution twice. Again, the type is a general solution. It does not come with any extra conditions. So let me go through my slides with you. I'm done with the example 1. We're on example 2 now. Okay. So the first derivative, that's why I told you the prerequisite is calculus. You should be able to differentiate and integrate things. If I differentiate this, I'm going to get 3e 3x. You know that. The second derivative gives me 9. If you're not able to differentiate exponential function, wahala oh. So I have to substitute 1, 2, 3 into the equation because I need all of it. So I start with u prime prime, that is 9e 3x plus twice of u prime 3e 3x minus 15 of u, that is e 3x. This should be equal to 0. So let's see. I expand. I have 9 plus 6 minus 15. 9 plus 6 is 15 minus 15ex. So 0 is equal to 0. And that shows that this is indeed a solution to a differential equation because it is satisfying the differential equation. It has to satisfy the differential equation. What is on the right hand side should be equal to what is on the left hand side. Okay. The last example, this will be a particular solution. Let me do the type first. This is a particular solution. We expect 1. Why? Because it comes with conditions. Okay. Again, the highest order here is 2, so I differentiate it twice. The first derivative gives me 2ex. This is a product rule, so you must know how to differentiate product rule. I already have my solution in my slide, so I'll quickly go through that. And that gives me, I maintain one and differentiate the other, plus I maintain one and differentiate the other. That is product rule. The second derivative, still on this one, I don't move back to y. Y prime prime is the same thing, so I have 2ex. I maintain one and differentiate. I maintain one and differentiate plus ex. I group like terms, I get 4ex plus xex. What is happening? Okay, so I now have to do the substitution. I need the y, so I take equation 1. And I need the y prime equation 2. I need y prime prime equation 3. Trust me, if you do the substitution very well, you end up getting 0 because of the negative sign here. So trust me, believe me, it is 0, which is indeed a solution to a differential equation. Take your time and do the substitution for this. But we are not done here. Because there's conditions attached, let me use the red to do emphasize or emphasis here. Because there's condition attached, your solution must satisfy the differential equation and the conditions given. We have satisfied the equation, it is indeed equal to 0. We have 0. What about the conditions? It says y at 0 is equal to 2. The solution says y is equal to 2ex plus xex. How do I verify that? So I set y to be 0. At y 0, don't forget this is the same as y at x equal to. Okay. I mean, whenever I see x, I substitute 0. I must get 2. So 2e to the power 0 plus 0e to the power 0. This whole thing goes to 0. E to the power 0 is 1, so I get 2, which corresponds to that. My arrow is pointing somewhere else. So this corresponds to that. So indeed it has satisfied the first condition. I'm not done. I have to do the second condition that says that y prime at 0 should give me what the condition? 3. So what do? I have to differentiate y prime first. I've already done that. It was we had 2ex plus xex plus ex. Again, y prime at 0 should give me 3. Let's verify that. 2 to the power e to the power 0. This gives me 0 plus e to the power 0. Any number to the power 0 is 1, so I have 2 plus 0 plus 1, and that is 3. Hooray! So it is indeed a solution to the equation because it satisfies everything about the equation. And this is how you test for solutions. And that brings me to the end of my lecture video today. So I have a trial table here. Let me look at the last point. It says verify by direct substitution if the given solutions are indeed solutions to a differential equation. I've already given the answers: false, true, 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 false, true. You can pause the video and verify these solutions if they are indeed true or false. Alright, so stay tuned for the last lecture video on the introduction to differential equations, and that'll be good. Enjoy the rest of your day.